Welcome to Chapter 5. In this chapter, we'll focus on how DIA data is processed within the HDExaminer PRO workflow. We'll start with how the software uses initial mapping runs to create peptide lists, then move into fault-tolerant deuteration measurements and binomial modeling. Next, we'll explore how fragment-level data builds confidence in peptide identity and measurement accuracy. Finally, we'll look at how statistical validation adds another layer of confidence to the HDX results. By the end of this session, you'll understand how DIA not only confirms peptide identity, but also enhances data reliability and reproducibility. Let's get started.
The HDX DIA workflow in HDExaminer is not unlike your typical HDX workflow, where you would still acquire an non-deuterated DDA mapping run. This is just to check digestion efficiency and to also ensure that the protein sequence coverage is good enough. From that, you would generate a peptide list that you would supply to your software. And in this case, you would also supply DIA data instead of MS1 only data. And so with a peptide list and a DIA data, the software will go through a few steps. The first step is to perform fault-tolerant deuteration measurements. Fault-tolerant is because we try to actually deconvolve MS signal in both MS1 and MS2 space. We do this by fitting a binomial expansion model to the observed data and then calculating the amount of deuterium uptake using the centroid mass of the model. This allows us to sometimes deconvolve overlapping signal from peptides that overlap each other on some isotopes. Next, we would measure the deuteration in MS2 space as well. And so this way we get our deuteration measurement for every fragment, which, as mentioned previously, is actually another measurement of the peptide itself. From the multiple fragments, we can then generate an MS2 deuteration model, which is depicted by the red dotted line. And this red dotted line most of the time will fit very closely to the peptide deuteration that we measured in MS1. And then finally, because we have all of these multiple measurements, we can do some statistics that allows us to automatically validate the peptide deuteration. So we can actually take subsamples of these fragments and then get deuteration differences between a state and a second state of a protein. And that way we can actually set confidence intervals on our Woods plots, for example. And these confidence intervals come from the variance in the different subset of fragments that we use as representatives of the peptide deuteration. And so after we form these normal distributions, then we can display the standard deviation on the Woods plot, which can't really be done with MS1 only data. Okay, so just to kind of wrap up, the DIA data enables us to do two things. The first thing is that we can confirm the peptide identity. So we have individual fragments of the peptide in all of the DIA runs. We can actually confer the peptide identity in every single one of these runs. So there's no question that the peptide we're looking at is the correct peptide and its identity is authenticated. And second, we can either endorse or override the peptide deuteration based on these fragment deuteration measurements. We would endorse it in cases where the peptide MS1 signal is clean and the fragments give us the same deuteration measurement. Or we would override the peptide measurement in cases where the peptide is completely overlapped and cannot be rescued from MS1 data alone.
In Chapter 5, we saw how DIA processing enhances peptide identification and deuteration validation by leveraging fragment-level data and robust statistical methods. Up next, in Chapter 6, we'll look at a specific case where MS1 analysis struggles, but DIA overcomes those limitations. You'll see how fragment ions in MS2 space can salvage measurements, even when peptides are heavily overlapped in MS1.